Swayam Prabha. Digital India. Educated India.
How did we, what were we doing? We were dealing with the 3n number of normal modes. Okay. For each operations, let us say for an operation R, let us say n number of atoms do not change places. Okay. So, what is going to be chi R? What is going to be chi of R? Oh no, do not violate Aufbau principle. What is chi of R? N n multiplied by n multiplied by what? Shall I call it chi xyz r? Will you allow me to call it chi xyz r? Is that what we wrote last day? Because I forgot, I do not remember what I wrote. Right. Remember what we did for BF3. Unfortunately, today is one day when I have not brought my laptop. But what did we do? We fixed unit vectors on every atom. We called them x1, y1, z1, x2, y2, z2, x3, y3, z3, x4, y4, z4. And then we performed whatever operation we had to perform. Okay. Think of C3 for example. When we applied C3, what happened? 1 moved to the original position of 2, 2 moved to the original position of 3, 3 moved to the original position of 1, right? And 4 remained what it was. And then I think we had worked out that entire 12 by 12 matrix there. Was it 12 by 12? Yes. We worked out that entire 12 by 12 matrix, and we had said that whichever atom changes position upon that symmetry operation does not contribute. Does not contribute to what? To the character. Do you remember that? Because they go off diagonal, right? And in character only the diagonal elements will contribute, right? Now, what do I get? What do I, what is it that contributes then? See, so for C3 operation for example, or 1, 2, 3, 4, only atom number 4 contributes, is that right? Mayak? Now, if atom number 4 is the only one that is contribute, what is it that we are using as the basis? X, Y, Z, X, Y, Z, right? This is how we had held it, or no? This is how we had held it, right? X below, Y pointing this way and Z pointing this way, and then we said that we rotate it by 120 degrees. So, basically what we are doing is we are working with a set of X, Y, Z for 4 only, and 4 is the only atom that does not change place. Okay. And how will this X, Y, Z transform? Exactly in the same way as is given in the character table, right? Right or wrong? Right? Dola? Fine. So, say that. Now, if I take what I am doing essentially is the n part clear? That only those atoms that do not change places will contribute, right? And then think of C3, that is what I am saying. Think of C3 in C3H, D3H, sorry, in D3H. So, in for atom number 4, what we said was this was X4, this was Y4 and this was Z4. Okay, you give it a C3 rotation. What do you get? Z4 remains Z4. I won't even draw it. Okay. What about X? Where does X go? This was X4, this was Y4. Where will X4 go? 90 degrees and then 30 degrees further. So, it goes here. This here is your X4 dash, right? This is 30 degrees. Where does Y4 go? I can cheat a little bit and I can simply draw a line that is perpendicular to X4 dash. And this angle will also be 30 degrees naturally. Understand? So, what is it that we are transforming? We are transforming unit vectors along x, y and z. Okay? So, what I am trying to say is, if you now look at the character table, the problem is I have to zoom in again. D3H, see what happens, Z, what is the character of C3 for Z? 1. And what is the character for XY for Z, for C3, sorry, what is the character for XY for C3 operation? -1, right. What I am saying is I can simply take those characters, isn't it? So, I am taking X, Y and Z together. So, you are basically adding 2 blocks. So, what will be the total character? 0, -1 from XY and +1 from Z. The total character will be 0. Now, think of what we had done at that time. Did we not get 0 after all that operation? Right? Yes or no? Did we get 0 or not? Right. So, what I am saying is this is how we got the 0. Number of atoms that remain unchanged upon the symmetry operation multiplied by character that you get from x, y, z for the same operation. Now, did you understand for C3? Okay, now let us think of something else. What about C2? Yes. This is my bad handwriting. Okay, got it. Now let us think of something else. Think of C2. We have drawn our molecule like this, right, and we have taken our C2 to be along, since I have other colors, I hope. This is a different color, yeah. You cannot make out, it is a different color. How about now? Which means that this camera is as colorblind as I am. Okay, fine, but I don't know how to draw it actually. Anyway, let me draw it again. This is my molecule. Okay. Then let us say if I draw it like this, you will be able to make out, isn't it? This here is my C2 axis, 1, 2, 3 and this one of course is 4. If I apply C2, then what will happen? 2 and 3 interchange places, 1 and 4 do not interchange places, right. Now what happens to the vectors? Where is x for 1? Where is x1? This is x1. Where is x4? This is x4. Do they change? They do not change. What about y1? y1 becomes minus y1, right? What about y4? That becomes minus y4. Okay. So, whatever happens to y1 also happens to y4, because essentially they are unit vectors that are parallel to each other, isn't it? So, now if I want the character, what will I do? I know what is the character for xy and for z for C2 operation. Okay, I will just read out from the character table here. For xy, for the character is 0 for C2, and for z the character is minus 1. So, what will be the character then? Minus 1 multiplied by 2, minus 2. Did you not get minus 2 earlier when we actually worked it out? Now, is it starting to make sense? Do you understand what you are supposed to do? What was next? Sigma V, no, sigma H. Sigma H. So, 1, 2, 3, this is 4, I will not even write. If you apply sigma H, then what happens? Which plane is sigma H? XY plane, right? So, now do you agree with me that x1 remains x1, x2 remains x2, x3 remains x3 and x4 remains x4? Similarly, y, what about y? Why do you not like y? After x you want to go to z, that is not very good. So, y, y1 remains y1, y2 remains y2, y3 remains y3, y3, y4 remains y4. So, whatever happens to one y happens to all the y's, provided the atom has not moved from its original position, right, and z changes sign. Okay. So, what had we said? We said we have 4 identical blocks, isn't it? Did we not say that the matrix is like this, transformation matrix? We have this 4 identical blocks, and what are the blocks? X remains what it is, y remains what it is, z changes sign. So, 1 1 1 1 4, isn't it? So, do not we get it by the same relationship, n into chi x y z r? Let us see what is chi x y z r. Can you read now? What is chi xy for sigma h? 2. And what is chi for z? So, 2 minus 1 is 1, and number of atoms unchanged is 4, all right. Okay. What is left? I am a little lazy, so instead of S3 let us do sigma V, okay, and I will not even draw now. Let us see if we can visualize it and think. You also do not draw. Let us see if we can do it in our minds. When I apply sigma V along 1 4, then what happens? So, how many atoms do not change places? And which plane is sigma V? No, in terms of x, y and z. Zx, right? So, what will happen to x, what will happen to y, what will happen to z? X and z do not change sign, y changes sign. So, what will be the character for each atom? 1 1 minus 1. So, 1, and how many atoms do not change places? 2. Do we get the same thing from here? Sigma V xy is 0, z is 1. So, 1 multiplied by 2. Understood? Are we all okay now? Okay? All right. So, finally, this is what we are using, right. We will write another slide. Chi of R is equal to N all right. So, chi of R equal to N multiplied by chi of x y z for R. What is chi of R? It is the character in the reducible representation. Okay. Which reducible representation? This, here we are talking about gamma 3n, isn't it? This chi of R, when we write this chi of R, we are talking about the reducible representation that we generate from the 3n number of coordinates that are there in the molecule, all right. What is n? N you know already, number of atoms that do not change places under symmetry operation R, upon operation R. And what is gamma xyz? This is going to come from gamma x plus gamma y plus gamma z from the character table. Okay. Now, can we do this? Then what did we say? That this is 3n, fine. What do I need to take out from this? How did I get gamma vib? Gamma vib equal to gamma 3n minus gamma trans minus gamma rot. Okay. So, what you could do is you could work this out character by character. What I can say now is that for chi vib R is equal to n into chi x y z of R minus, will you allow me to write chi x y z R once again? Chi x y z R is the character for the particular symmetry operation R in the representation that you generate by combining the irreducible representations of x and y and z. What is gamma trans? Is gamma trans not gamma x plus gamma y plus gamma z? Are we all okay with this? Nishit? Sure? Any question? Any doubt? Please ask now. All right. So, instead of gamma, for gamma trans, I can write chi xyz. So, do not forget what we are doing. This line is about the total representation. This line is about individual characters. Okay. So, what I am saying is chi vib R, the character for symmetry operation R in the reducible representation containing the 3n minus 6 normal modes of the molecule is given by n multiplied by chi xyz R, okay, minus chi xyz R minus chi Rx, Ry, Rz, R. So, this can be simplified as chi vib R is equal to n minus 1 chi xyz R minus chi Rx, R y R z of R.